So when we apply the force the P1 as F1 is developed, now when the force horizontal force applied to the block is P2, the friction also increased to F2, and earlier for F1 the angle was delta 1, angle of obliquity, and now when it is F2, this delta 1 become delta 2. Okay, so in this way the force is applied from P1, P2, P3. Okay, and still the block is in the rest condition. That means the friction is also increased proportionately. Okay, and this delta is also increases. Okay, now at a particular the magnitude of the P, beyond that the certain maximum force is developed. It's called as a mobilize. It means the friction between these two is fully developed, fully mobilized. Okay, and at that time you can see the last one, that is the F. When final load is applied, suppose a P, and that time F is the frictional force developed. So delta become delta 1, 2, 3, it become a maximum. Okay, the meaning is that with a sudden increase in the small increment in the P, the block will move. Okay, and as block will move, so it means that the maximum friction was already developed, so the angle was it become a delta max. Beyond that it will not increase. Okay, so if you consider that limiting conditions, okay, it is just on the verge of disturbing its equilibrium. Just before the moving, the maximum stress developed is that F. Okay, so in this feature P is the shear force, F is the frictional force, delta is the obliquity angle. Okay, now this delta, when it is less than phi and greater than 0, it will be delta 1, delta 2, delta 3. Block is a rest condition. When delta is equal to phi, it is an impending condition, and when it exceeds delta is greater than phi, the block will move. So if you see the same condition is geometry here. So the last value of F and the N, and angle is delta. If I take tan of delta, then it is F opposite upon this adjacent, F upon N. This is also called as a coefficient of friction, that is mu. So therefore the horizontal the component is F, that is a frictional resistance, is equal to N into tan delta. Okay, now friction takes place only at the contact surface, and if A is the area of that contact surface, okay, which is shown earlier in this shaded area is A, that is where the contact between the bottom plane and that body takes place. If I divide this expression of F by that contact surface A, F by A, N by A. Now F by A, you can see here direction of F is horizontal, parallel to the plane of area A. A is called as the shear stress, and N is a vertical component, and perpendicular to that area is A. It's called as a normal stress because it's force upon area which is perpendicular. Shear stress, force upon area. Area is in the direction of the force, so that is a shear stress. So this relationship can of a force can be expressed as a stress, as tau is equal to sigma tan delta. Now if block is just on the verge of failure, the maximum impending condition develop, okay, at that time the delta become the maximum. Okay, and suppose the block and the plane are of the same material. Suppose the block is also soil and the failure plane is also soil. So in actual condition is like a part of say hilly area, suppose, and part of the portion gets slide down. so the portion which gets slide down is like that body, and the plane on which it slide down is a failure plane. Okay, so in that case, when same material slide over the same material, then it is delta is equal to phi. So therefore this delta is replaced with the phi, and phi is called as angle of internal friction. Okay, it is called as, also called as angle of internal shearing resistance, or earlier it is also called as a soil friction in general term. So the tau is equal to sigma tan phi, and this applied force P divided by area, which we get the shear stress, and from F we get a maximum resistance, that is the strength. Okay, so limiting condition is that the tau and shear strength both are equal. Okay, that is the limiting condition. So we can also write tau as a S. The meaning is that external stress and maximum the strength developed on that surface is the shear strength S, that is normal stress into tan phi. So this is the perfect expression for a pure sandy soil. This concept is very similar to the sandy soil. Okay, originally concept of the friction of a, suppose a different body like a wood is getting slide over this other area, maybe another type of the area, maybe glass or any other thing. Okay, so this expression is exactly similar to the soil when it is a sandy soil, or it is called as a cohesionless soil. There is no a bond between the two particles called as a cohesion. In that case, this expression holds good. Okay. Now in case of a clay soil, this expression has to a little bit modified, because in clay, you can see the figure here, the particle they are bonded together. You must have seen that clay, when it is partly saturated or dry, it forms a group of particles called as a flock. Okay, so why these particles are together? Because there is a force of attraction, intergravitational force between these two, that is called as a cohesion. To separate this cohesion, okay, here extra shear stress is required, extra force is, that is P is required and it is exactly in the direction of that P, so it is directly added to this equation, okay, as a cohesion, and this cohesion is added in this equation. The cohesion C is added because it is a bond between the two particles, and to break that bond extra force or stress is required. Okay, so directly that additional stress is called as this cohesion is added here. So it is a cohesion is a small c, okay, and it is a like pressure, and unit is say kg per centimeter square or kilonewton per meter square. So finally the expression is S is equal to C plus sigma tan phi. This friction as we discussed, or we can see the expression, that is tau is equal to S is equal to C cohesion plus sigma normal stress into tan phi. Phi is the angle of internal friction. So basically friction and the cohesion, these are the two important parameters, and of course with the normal stress. So friction means what? Friction is because of, so the equation contributes the shear strain because of frictional resistance due to the sliding or rolling of the particle. So when the P load is applied, okay, and N is already there, so because of that the particle try to roll each other, or particle try to slide each other, and because of that the friction takes place, and that's why we also get a angle, that friction. Another is the interlocking of a and bridging of the solid particle. Okay, sometimes the soil is loose, for example sand is loose, so because of that the force, external force, so the gap decreases, so wide ratio decreases, so there is an interlocking also is there. Okay, sometimes the particle are like a rivet, suppose the angular particles like aggregates, and in that case if the force is applied on that entire soil mass, these particles are riveted each other. Okay, it means they have a something like angular edge, and which insert into the voids of the other particle. To overcome that, when the movement takes place, there is an additional interlocking friction takes place. So in addition to that, the cohesion or the adhesion. Cohesion means when the same material, adhesion means the two different material, that is the adhesion. Two different material means like a retaining wall. In a retaining wall there is a wall, and backfill is the soil. So when friction takes place, it is we also call it as a adhesion. When friction takes place between soil to soil, then it's called as a cohesion. So these are the important parameter. Other parameter also on which this shear strength depend: change in moisture content. It's very important, particularly for a clay type of soil. When clay is partly saturated or dry, then in that case you'll find that a friction takes place within the particle is a maximum, because the surfaces are dry. As moisture increases, when moisture increases, the friction decreases, and when moisture is the maximum, even it is close to is the liquid state, liquid limit, then friction is hardly anything, which is very minimal. So that is, change in moisture plays the most important role in case of a clay. Okay, pore pressure also is one of the important thing, as we have seen in the consolidation, that is spring analogy. Okay, when load is applied and the wall is closed, entire load is taken by the water. Okay, so no load transfer on the spring, it means no effective stress transfer on the spring, and only on the water. So the maximum pore pressure, the friction takes place in this case is the less. Also called as a structural disturbance. For example, if I take a undisturbed sample like a core cutter and test it, and then I remold it and again test it. So undisturbed sample has a higher shear stress, whereas a remolded sample, again I prepare the same specimen of remolded sample, same soil, it takes a less resistance. Fluctuation of the groundwater level also play the important role. When the groundwater table is there, the soil becomes submerged and its normal stress decreases, as well as this friction also decreases. And there are other factors like chemical and environmental condition. So the in that shear strength equation, the Coulomb's equation, these various normal stress, C5 combinedly called as a total shear parameter. In Coulomb's theory, they are not influenced by the effective stress, they are influenced by the total stress, that is the shear parameter. C is the cohesion, or we can general pressure or stress, kilonewton per meter square. Phi is the angle of internal friction. Okay, so one of the oldest equation, 1776. Okay, later on in 1900, this Otto Mohr, hypothesized a criteria of failure. Okay, means he again studied this Coulomb failure criteria, and he modified it. Okay, and he recommended this following point. The first, failure of material essentially due to the shear. Yeah, this statement is very important, particularly for a soil. If I take a metal or any other the rigid material, mostly they fail in the bearing also, fail in compression also, depending upon the direction of stress, tension also. Okay, but when the load is applied on a soil, then failure is because of a shear. Okay, so other rigid material or elastic material also, it fails in either in a compression or a tension. but soil essentially fell in a shear. The criteria of the shear stress on the failure plane depends on the normal stress and material properties. Okay, so any body of certain material, it fails. When it fails, the failure entirely depends upon what is the norm. Then failure takes place inside with a certain failure angle, what we call it as a crack, suppose. Okay, along that crack or failure plane, the critical stresses act, and because of that failure takes place. It's not directly the external loads are responsible, they are only the direct measurable forces or stresses. But inside on the failure plane, one stress parallel to one stress perpendicular to the plane, failure plane, is called as a normal stress, and parallel to that is the shear stress. These two are developed. Okay, and these two are they are of a different magnitude, but when failure takes place, then they are in a critical states. Okay, so critical shear stress on the failure plate depends upon the normal stress and material. So if normal stress goes on increasing, okay, as we are seeing, the tau is equal to sigma tan phi, it means that this tau is also increases. Okay. For example, if weight of the soil block is higher, so definitely the shear required is higher. Okay. We take a simple example, like a truck, empty truck, and when the driver starts, he has to press the accelerator slowly, because as it is empty, the normal stress acting on in between that the wheels is a less, and therefore at the contact surface, tire and pavement, the friction is less. When it is a loaded truck, definitely the driver has to press more accelerator because he has to overcome the more stress. Okay, so that is exactly how here the phenomenon takes place. Mohr's Coulomb criteria. Okay, the ultimate shear stress is determined by the stresses on the potential failure plane. Okay, as I said that in any body, when external stresses act, maybe normal or shear, okay, failure takes place along certain crack, we call it as a failure plane. So before that, this failure plane orients. Okay, suppose alpha is a failure plane, so alpha is about 30 degree. So because of the earlier magnitude of the external stress, it may be some 20 degree, 25 degree. So plane goes on rotating, and on a plane, when the critical stresses act upon, okay, the normal stress and shear stress, so failure takes place. So failure takes place on that particular plane, and that is called as a potential failure plane. Okay, so first point was with respect to the normal stress. Second point with respect to the failure plane inclination. And third important point, when the material is subjected to three-dimensional principal stresses, okay, sigma 1, sigma 2, sigma 3, the intermediate principal stress sigma 2 does not have any influence on the shear strength of the material. As we have studied in the last lecture, that major principal stress and minor principal stress, in between there is also intermediate principal stress, that is sigma 2. Okay, but as per this theory, that the sigma 2 is not responsible for the failure plane. That is the meaning. Only sigma 1 and sigma 3 are the participatory in the. Usually we can also say that sigma 2 also equal to sigma 3. Okay, we'll see in the further. Okay, so this is written here. 2 is equal to intermediate principal stress is equal to minor principal stress. Okay, so mathematically shear external shear or shear strength is a function of the normal stress, and equation can be C plus sigma tan phi or sigma tan phi depending upon the type of soil. Okay, Now, if you see these two diagrams, they are almost same. Their relationships same from the expression that Coulomb score. If I plot a one second. So, if we plot that relationship, that is the equation S is equal to C plus sigma tan phi. X-axis is the normal stress sigma, y-axis is the shear stress tau. Okay, so Coulombs give the straight line. Okay, and suppose I keep both axes to the same scale, I can directly measure the angle. Okay, you can even extend this line, not necessary to pass 0, then measure the angle. So this angle is the angle of internal friction, and this intercept, okay, in the equation it was S is equal to C, means it is R tau shear stress is equal to C plus sigma tan pi. So it means shear stress is equals to the cohesion. Okay, so it is plotted in the direction. So intercept gives the a cohesion. Okay, and angle gives the angle of internal friction. Okay, so this is the Coulomb theory, and what Mohr plotted the curve, what he found that in the beginning the relationship is same, the sigma versus tau, but this curve, instead of straight line, it is a curve. Okay, now when it is curve means mostly a non-linear curve. Okay, but the analysis of this non-linear curve is somehow very difficult, and what type of, not necessarily all soil shows this curve, particularly a dense sand or over consolidated soil gives a core failure. Okay, but if you overlap these two, then the percentage of error, particularly other soil like a medium to loose, they are very minimum, and for a dense it is slightly more but still acceptable. And to make the theory simplicity, okay, even though it is a curve, we still follow a straight line curve like this. Okay, so the Coulomb's curve, Coulomb's theory is generally called as a Mohr's-Coulomb's theory. Okay, considering a straight line. Only when we say Mohr's theory, okay, Mohr's theory gives us a curve failure surface. That is the difference. But still in practice we use a straight line, that S is equal to C plus sigma tan phi. Now we can also explain this theory in another important concept. Consider this failure plane which is plotted here. Okay, this is C and this is phi, and suppose I could able to plot the three circles, half Mohr circle. One is A, one is B, and third is the C. So A, B, C, three half circles are there. Okay, so what is the state of A, B and C, that now we'll discuss, which is the one of the important part of this Mohr's-Coulomb theory. Now Mohr circle A, this green one, shows that it is below the failure envelope. This is called as the failure envelope. S is equal to C plus sigma tan phi, Mohr-Coulomb's failure envelope. It indicates that, this A indicates that the principal stresses on the plane are less than that of a critical stress. Failure plane indicates means that anything which touches or any point on the failure plane indicates it is fail. Now circle A is below, that means the soil or soil sample representing the A is not in failure condition. So critical stresses are not developed, or they are much above. These are the critical stresses, and actual stresses are this. So this is called as a stable condition A. Soil is in stable condition. Okay. Now when it comes to the B, you can see it is a tangential. The circle is tangential at a point B, and as it is touching to the failure plane, so this is the limiting conditions. Okay, it means it is on the verge of failure. So P indicates it is a condition. Uh, the soil is just on the verge of failure, and the failure plane is the alpha. You can see this is the failure plane. Okay. So A is a stable condition, B is a limiting condition on the verge of failure. And what about the C? What it indicates that the stress applied is greater than the failure envelope. Failure envelope means what? Soil has exhibit entire strength. Whatever the load is coming, whatever stress is coming, it has been resisted. So this line indicate is the maximum resistance. That is the shear strength. Okay. So here the stress applied is above. So it means the C condition cannot be exist, because the stress applied such that before it goes to the sea, the soil has exhibits its entire strength and it fail before it reach, before you apply the additional stress. Okay, so C does not exist. A is the stable condition, B is the limiting condition, C does not exist. So that is the meaning. The concept is that any point above this, it does not exist, or failure condition. On that plane it is a failure condition. Any point below that indicates a stable condition, or soil has still potential to resist the additional stress. This is what is explained. So on that line we get this limiting condition, the shear stress, which is at which the failure plane is alpha. Okay, in the figure, at that time, on this point, on this line, the shear strength is S is equal to C plus sigma tan phi. So therefore we can write tau F is equal to S. Maximum shear stress at the failure is equal to the shear strength of the soil. The hypothesis of this point of tangency define the failure plane. It's correct. Okay. This is what we explained in earlier condition. Now, Mohr's Coulomb theory with the effective stress principle. Now, in the earlier Mohr's Coulomb equation, seen that S is equal to C plus sigma tan phi, where C and phi called as a total shear parameters. Okay, or okay. In that also the sigma is the total normal stress. Okay. Now with the effective stress concept, see the effective stress concept which was given by the Terzaghi, okay, much later, that is in 1920 or 24. This concept which brought a total revolutions in the soil mechanics. Okay. So this it is observed that on the many specimens of the clay, a failure takes place not at the total stress but because of the effective stress, provided there is a condition for the effective stress. Okay. So with the effective stress concept, the equation can be now revised as S is equal to shear stress at failure is equal to shear strain is equal to C dash, the effective cohesion. Okay. Effective normal stress on the failure plane alpha. Alpha represents normal stress on the alpha, and phi is the effective angle of internal friction, or C dash and phi dash combinedly called as effective shear parameters. Sigma dash or sigma alpha here at failure. That's the effective normal stress on the failure plane alpha. The normal stress sigma alpha and shear stress on the plane alpha with the major principal plane can be expressed sigma 1 and sigma 3 dash as we know in the Mohr circle concept. this sigma alpha is given by, suppose, a sigma 1 plus sigma 3 by 2. It means the element is not subjected to the shear stress. Tau is 0 and ABCD boundaries are nothing but a principal plane. Okay, so like a sigma y and is the sigma 1 dash and sigma x is the sigma 3 dash. Alpha is a failure plane. So normal stress equation, and this is the shear stress equation. Okay. Now this is our strength equation, and these are the stresses, that is normal stress and tau on the failure plane alpha. Okay, for example, this is the failure plane alpha, and this is the normal stress, and this is the shear stress. Shear stress is not shown as effective, that you have to remember. It's a normal stress only. You can show it as effective because this is the applied one, this is the actual development. Okay, now substituting in this equation is sigma alpha dash from this equation 2, you substitute here. Okay, so these two terms multiplied by tan phi dash, so you can see here c dash as it is, tau f is written as tan phi, then you multiply tan phi here, tan phi here. Okay, this is the strength equation, and these are these two external stresses which are responsible for the failure. It means applied stress or applied shear stress, okay, and shear strength, when they are close, it means on this line of failure plane. Earlier we have seen in the, okay, like this circle, when both are tau f and tau were close, then it's a limiting condition. Okay, when they're exactly same, possibility of failure, or when their difference decreases, then also failure chances are more. The most dangerous plane is the plane on which the shear stress approaches to shear strength. When tau approaches to the shear strength, then it is the most dangerous conditions. And other way, we can see that the strength and applied stress in shear, when their difference is less, then there is a possibility of failure. Okay, so subtract that tau f equation, this tau f, okay, and subtract this term, so minus this terms, so you get here, this is the minus terms. Okay, and now you can see here see that you get it after failure. Okay, sigma 1 sigma 3 dash the principal stress. In this case they are the external stresses, so that also we know. Okay, phi is a fixed one. Every soil in that state has a one fixed frictional angle. What is that? Alpha. You can see when alpha is less than that alpha, critical suppose, or alpha, failure will not take place, and angle will also be less suppose. So when that angle reaches to that alpha, then only failure takes place. On that failure plane, we get a sigma alpha and tau. Okay, the meaning is that alpha is a variable in this equations. Okay, if alpha changes, entire stress condition changes. Okay, so if I differentiate this difference, shear strength and shear stress, with the variable that is alpha, okay, and I go by that maximum and minimum case, as we know in a simple mathematics. So you can differentiate. So variable is only alpha, so this is constant, and this become a minus 2 sine 2 alpha. Okay, and then this term again minus 2, this is constant, minus this constant 2 into cos 2 alpha, equating this to 0. Okay, taking the common terms, alpha one side, okay, and phi other side. So you get, and simplifying, you get alpha is equal to 40 plus pi by 2. This condition is the revolution conditions. Okay, we change the concept of the failure, the meaning of this alpha. Now it is 42 alpha means 90 plus pi, alpha means 45 plus pi by 2. The relationship between the failure plane and this is the failure plane and angle of internal friction, if it is represented in the Mohr circle, how it represents? You can see the Mohr circle, this is the C, angle is phi. Suppose this is the failure plane, already we have drawn this, we know from a simple test. If this represents any failure point, okay, I can draw a perpendicular and draw a Mohr circle. So it is a tangential, that means there is a failure. This angle is total is alpha. If I join this angle to the center of the circle, this is the center, then this become 2 alpha. Okay, so here you can see this is the radius or the maximum shear stress, and this is the shear stress at failure, tau f. If I join this maximum shear stress line, the angle is 45 degree and this small angle is 5 by 2. So total angle is, this alpha at failure is 45 plus 5 by 2, or here it is 90 plus 5. You can see 90 plus 5 is 12. Okay, so this the Mohr circle here represent the most important part. It is you can see here at failure the shear stress is tau f, which is less than the shear stress, maximum shear stress. When the shear stress is maximum, the failure plane, that alpha is 45 degree. When shear stress is here at tangent point, it is 45 plus 5 by 2. Okay, so I have two planes for two different shear stress magnitude. Okay, so it is observed that for any combination of the sigma 1 sigma 3 dash, failure will occur when Mohr circle touches the failure envelope here, not at any other point. Where it is tangential, there failure will occur. Okay, another important condition you find that it is noted that the shear stress tau f at failure plane, that is alpha, is not a maximum shear stress act on the plane inclined by 45 degree. Okay, so meaning is that the shear stress causing failure, okay, is not a maximum shear stress, and plane, or other words, plane on which shear stress is failure is a different plane, that is 45 plus 5 by 2, not 45. Okay, at tau maximum which is inclined by 45 degree, that is the radius of circle, sigma 1 dash sigma 3 dash 2, then why does not the failure occur on 45 degree plane? It's a question mark. It cannot, because the plane 45 degree on which the shear stress act has a greater shear strength, the point M, than that of the tau max. Hence, it is concluded that the failure plane alpha does not carry maximum shear stress, or a plane, okay, 45 degree on which the shear stress is maximum is not a failure plane. What is the meaning of these lines? A plane on which failure takes place, okay, is not a maximum shear stress. Okay, or plane on which the shear stress is maximum is not a failure plane. This is not a failure plane, but failure plane is this. Or a failure plane is one on which the shear stress is not maximum, or the shear stress is maximum on that plane. That plane is not a failure plane. Now why this 45 degree or tau max is there is not a failure plane, because you can see failure takes place only when the failure envelope touches the circle. Okay, at this point, even though the shear stress is less, the failure takes place because it is tangential. It means the shear stress and the shear strength both are equal on the verge of failure. But whereas even though the external applied stress, that is tau max, is more than this, but failure is not takes place. Why? Because the shear strength envelope is above, say let us say point M, which, okay, it means the soil has a more strength than the tau max. You can see from point M to this, shear strength available is greater than the shear stress maximum. Therefore, this green line 45 degree is not a failure plane, but this alpha plus 45 degree is a failure plane. That is the meaning of these two sentences which are written here. So all we discuss about the Coulomb's theory, Mohr's Coulomb theory, and the Coulomb's equation or Mohr-Coulomb equation, S is equal to tau is equal to C plus sigma tan phi. Now how to determine that shear parameters or shear strength? Some of the experiment gives shear strength directly, or some gives the parameters. Okay, so the measurement of shear strength. Shear strength can be measured in the laboratory as well as in the field. Okay, so here laboratory tests are given, as it is discussed here, that most of the tests they give the parameters C and phi, while some tests gives you the direct shear strength. Okay, so different laboratory tests are the direct shear test. They also called as box shear test, because the test is conducted in a box. Direct shear test. Direct means the stresses acting on the predefined failure plane. Here the failure plane is predefined, horizontal. So the stress is acting directly on that plane. So that is called as a direct shear test. Then triaxial shear test is a much improved test. Earlier it was only useful for research. Nowadays also used in the practice. The unconfined compression test, in certain condition, that unconfined compression test, you don't require the stresses acting on sample in all directions, only vertical, just like our cube testing, okay, which also we call as uniaxial. This is similarly unconfined compression test. Okay, and sometimes undisturbed sample on the test is conducted on a very soft soil, because that soil you cannot make a specimen, it will be disturbed or failed by its own weight. Such a soft soil, particularly soft clays or some very soft clays, okay, the vein shear test is conducted. It is both laboratory as well as the field. Okay, commonly done it is a field one, also cross check with a laboratory test also. The principle is same. Now about test, the result they gives about test, either shear parameter or strength, is highly dependent upon the physical properties of the soil, like a unit weight, void ratio, moisture content, etc. The one most important thing is the parameter on which this test depend is the drainage conditions. Okay, is the one of the most important parameter. After that spring analogy concept we discuss. Okay. Because these tests can be done in a different drainage conditions. So what are these drainage conditions? Okay, three important drainage conditions are there. First drainage condition is called as unconsolidated undrained condition. Okay, now this drainage, for example, direct shear test can be conducted in a unconsolidated undrained condition. Triaxial test also can be conducted in this condition. So this when you conduct a shear strength test, it has a two part. One is related to consolidation, second is related to the shear. Okay, when we don't allow the consolidation of a sample and we apply the shear, and failure takes place in second part when you apply shear. Okay, and whereas the first part actually gives a stability, more stability if it is allowed to consolidate. So in this first word you miss, no consolidation is allowed. As soon as the load is exerted on the sample, the shearing is start. Failure towards the failure, the sample moves. So no consolidation is allowed under the load or external load. Okay, also no drainage is permitted throughout the test, so that's why it is undrained. Unconsolidation means no explosion of water, and during shear also no drainage is permitted, so it is also called as a undrained test. In short, this is very quick test, also it is called as a quick test. Okay, this test can be performed in a direct shear test. Test also can be performed, okay, using the triaxial shear test. Unconfined compression test by default is a undrained test. No drainage is permitted. When shear itself automatically become a undrained condition. Yes. Okay. Now, what are the conditions when we conduct the undrained, say, direct shear test or undrained triaxial shear test? Okay, what are the situations? And before that, you can see here the test in a direct shear test. This type of condition, to maintain the condition, is difficult. Okay, so particularly for a clay and all, it is very useful because the loss is less, but for a sand it is very difficult. It cannot be maintain such conditions in a direct shear test. Okay, so the in this test there is nothing like to wall to control the Mohr pressure or drainage. Okay, only the rate of strain, rate at which the soil is failed, controls the drainage. Okay, when I apply faster rate, then the soil has less time to drain the water, so automatically undrained condition is there. Okay, this is particularly very useful for a clay. So in short, this drainage condition is such that the entire test takes place very short time. Okay, we'll discuss in detail. Okay, now when we require this is required particularly design of a foundations. Okay, now why it is required? If the foundation resting on such a soil where the pore pressure develop, okay, but they dissipate at a very longer period. As we know, in consolidation test, that T90 is obtained. Okay, suppose T90 gives me a 5 years or 10 years. Okay, and application of load means if I am constructing a building, suppose G plus 5, the total time required maybe 1 year, 1.5 years. Okay, so time of loading is much faster as compared to the time of drainage. Then undrained condition is developed. Another condition is that if I am constructing an embankment, very fast rate. Okay, embankment is done in a layers. I am placing a soil in layer, but very fast, not allowing any wetting period. So consolidation period. So what happens? The load applied is much faster on that foundation soil, which has less time to drain. Therefore, automatically undrained condition. So in these cases, the test is carried out as an undrained condition, and those parameters are used in the design. Now, second condition is the consolidated undrained condition. It is one of the most important conditions also. Soil sample is fully consolidated under the applied stress, as soil is consolidated, it means the drainage is permitted. Then in second part, the shearing failure is observed at undrained condition. Means first part the sample is allowed to consolidate. Second part, the rate of strain was such a fast that no time is allowed for soil to drain out the water. Okay. So the second part is something like a similar to the first condition, undrained condition. So in the first part, consolidation, the water is drained out. Okay, it's just like a consolidation test. We keep the one load for 24 hours, suppose. So water is allowed to drain, but then we apply shear stress such that failure takes place in 5 to 10 minutes. Okay, and there are many applications of these conditions, this type of test. Okay, now as I said that in a box shear test, suppose, or generally rate is such that during a shear it should be fast application of shear stress in a strain control unit. So for example 1.25 mm per minute is considered to be a faster rate, so that no drainage is allowed during the second part, that is a shear. Example, sudden drawdown of the embankment. Okay, embankment dam, this is suppose the embankment dam. In this, suppose these are the two levels 1 to 2, and water is allowed to. In an earthen dam, what happens when water table is suddenly drawn down in certain conditions? For example, water is required for drinking purpose, irrigation purpose, or sometimes it is quickly diverted in the canal. Okay, or for hydrothermal, that is generation of power. Okay, for any given condition, if water table is suddenly drawn down, so okay, or drop. Now here what happens in earthen dam, outer portion is compared to inner portion called as core. It is highly impervious, so clay soil is used. Outside maybe granular soil is used. So because of the higher permeability, the water is quickly drain off from the outer, but in inner part still it is in the core even though water is drawn down. So because of that, the high pore pressures are developed. Okay. So this core or entire dam is already compacted or consolidated, fully consolidated, and suddenly when drawn down, okay, the possibility of this failure condition takes place. This portion may slide down, okay, quickly. So therefore undrained conditions are developing second part. Okay. First part is already consolidated, so that's why it's called as CU. So the parameters in these conditions C and phi are used for the stability analysis of this dam. Another example is that suppose this is a clay strata that, okay, as a foundation, and embankment 1 is already constructed. Now embankment 2 is freshly constructed and very quick. Suppose when one was constructed, suppose it is done in a layer. Suppose it took a 5 month or 5 months or 6 months. Okay, slow rate. But this has done in few days. Okay, 10 days, 15 days, very fast. So what happened? Because of the fast application of Mohr, the pore pressure developed is, okay, is very high pore pressure. So rate of loading is faster than the rate of drainage of water. Okay, so therefore this part is already consolidated, but sudden application of load may possibly that it may fail. Okay, so here the consolidated undrained shear parameters, that is C and phi, are used for the stability analysis. Okay, this is one of the most important condition. In this condition, in the laboratory test, the pore pressures are measured, okay, and that plays an important role in finding out the shear parameters C and phi. Another example is that this is a natural surface, okay, part of a hill, maybe very gentle slope, and suppose a small embankment is constructed, sometimes called as a check dam or something like that. So it is a rapid construction of embankment. Okay, so what happens? The load exceed, and this may fail like this. Undrained condition is developed in second part. The hill is already consolidated, so therefore it is CU parameters are used for the stability analysis. And third condition is consolidated drain CD test. Okay, it is similar to the earlier. In the first part is same, sample is consolidated to the applied state. Okay, first part and second part, then shearing start, but shearing start at a very slow rate, because if the rate is faster, then pore pressure is developed. So in this case, no pore pressure is allowed to develop, neither in consolidation nor during the shear. In both the stages, the pore pressures are zero. Okay, so therefore the rate of strain, you can see, is very slow, because no pore pressure should develop, 0.00125 mm per minute. But this test is a very slow test. Okay, for example, I want to conduct a direct shear test. Minimum 3 samples to be conducted. The first sample, after assembling, has to allow to consolidate, just like consolidation test. For example, we keep 24 hours the load. Okay, and after that the shearing start at very slow rate, so maybe 4 to 6 hours are required. So one sample will require 1.5 day at least. Okay, so then second sample, third sample, so 1 week is gone. So therefore this test is a slow test. This is also called as a slow test. Undrained condition, first one called as a quick test, where the test is completed within the 5 to 10 minutes. The rate of shearing is such that there is a failure takes place quickly. Here rate of shearing is very slow, that the failure takes place after a long time, because no pore pressure is allowed to develop. So in practice, what are the conditions? Similar one, like again, this is a suppose a compressible strata like clay strata, and embankment is constructed. It is a huge embankment, but it is done in a layers. Each layer is constructed and allowed to keep as it is to consolidate the strata, like first layer. Okay, then wetting period, second layer, wetting period, third. Okay, it means the rate of loading and rate of drainage of water, they are maintained, so no extra pore pressure is allowed to develop. So here CD test CD shear parameters are used, okay, called as C suffix D, phi suffix D. Okay, or the excavation, suppose maybe excavation and natural slope, maybe are used canals. Okay, but excavation is done in the layers from top to bottom, like very slow, so no failure takes place. Okay, then steady state seepage. This is called as a full supply level, or HFL, high flood level, in a suppose a barrier or a embankment dam. The water goes on seeping, because this is also a soil material, but this is a very steady state, not so fast like earlier. Therefore the CD conditions is developed. So this is how the three conditions which can be observed in the direct shear test or in triaxial shear test. Other two, they are the fixed unconfined compression test. It is always undrained test. Main shear is also something similar to the undrained test. Now we'll move to the first laboratory test, that is the direct shear test, DST, or it is also called as a box shear test. As I explained, shear takes place in the box, that's why it is called as a box shear test. And direct shear means the plane of failure is predetermined horizontal, and stresses are directly stresses acting on that are measured directly. That's why it is a direct shear test. Okay, now it can be conducted in the all three conditions. Okay, but the best condition is that the CD condition. It gives a perfect shear parameters, because in this stage there is no like a wall or something. Water is free to drain. It depends upon the permeability of soil and rate of loading. Now let us see the apparatus. You can see this, there is a shear box. This combinedly called as a shear box. It is the upper half, it is the lower half. This is a steel body. It is open at bottom and top. These are the studs to carry the different blades. This is called as a support, called as a yoke. So the load is measured on this. It is transferred here and can be measured. That's why it is a solid section is used. Okay. This part is placed on the lower part. Okay, same size. Now this the area of this is the fixed, because this is available in a small size or the greater size, large size. Small size is 6 centimeter by 6 centimeter. It's a square, 6 centimeter by 6 centimeter, internal. That size of sample is fixed. And height is 20. That we'll see how to adjust. These two are tied together with the help of a pin. This is called a shear pin. This goes to one hole here, second hole. It passes here and here. Two pins are sufficient. Other 2 points, there are the screws which are placed here, and that is used to lift this upper part over the bottom part by just 1 mm to avoid the friction between the metal. Okay. This is the base plate. You can see these studs are there. These studs are not required here. The studs are required here. These are not required. So there are 2 here, 2 on opposite sides. This plate is rest on this. There is a slot here. Okay, so this is a base plate. Then this is called as a serration plate or a grid. Serration means these are the lines. You can see in the cross section. There are 2/3 cross section. This form a lines. Okay. So this plate is placed in the box. This is placed here. So this is placed above the base plate. Now these line directions will be such that it should be perpendicular to the shear force. Why? Then because it is like this, perpendicular to shear force. So okay, this is a parallel. The shear force is perpendicular, gives the maximum friction, and that's why this plate is placed here such that here the direction of shear is this. So this grid plate is placed like this. In a lower part, it goes to lower part. Okay. The normal stress is applied with the normal force, which is with the help of a plates. They have a slot. That's why called as slotted weights. Okay. Now we'll see the box, the arrangement. This is the, as we have seen, that 2 part, upper half, lower half, and this is that the yoke. Okay, and this is connected with a shear pin here. The pin has to remove. The pin is placed here. Pin is placed here. Okay, this is the base plate. Sometimes porous stones are required in CU and CD condition. Then porous stone. Otherwise, they are not provided. Then this is the serration plates, and in between the sample. So sample is sandwiched or covered between the 2 serration plates and porous stones if required. These serration plates are the 2 types. One is a solid, second they are the porous. There is a hole in between 2. So there is a hole here. In CU and CD condition, consolidated undrained and consolidated drain, the porous grid plate is used or serration plate is used. At that time the porous stone is required. If it is the undrained test, then this is the solid one, no porous stones are required. We'll see in details. Okay. Other equipments you require ancillary equipments. These called as ancillary equipment: proing ring, dial gauge horizontal, dial gauge vertical. These measure the force and displacement. That's why they are called as ancillary equipment. Proing ring is in general is a very simple concept. It's a metal ring. Okay, inside similar dial gauge is already fixed and they are calibrated by the manufacturer. Okay, means on this ring the load is applied on either direction by manufacturer, and the displacement is measured with the help of this. It is very small within elastic limit, so that is measured with the help of dial gauge. Okay, so a chart is available called as a calibration chart, which gives what is the incremental load like a 1 kilonewton, what is the deflection in the ring recorded by this. Okay, suppose 20 units, then 2 kilonewton, say 25 units. Okay, so this chart is available. Suppose last is a 20 kilonewton, it means the capacity of this is a 20 kilonewton. So the different capacities are available: 20, 50 kilonewton, maximum 1 ton, 2 ton also. You have to select it as per what is the state of soil. And these are a dial gauges. Okay, you can see these are fixed. These dial gauges are used to measure the displacement. This is a plate attached to this box. Okay, this outer box you can see it has a slot here, solid slot, and this one. This is the outer box, or called as a water jacket. Okay, and this is the plunger. Force is applied by this motor. Okay, so this motor apply a constant rate of the shear force. Okay, so this apply here the F, which is measured here. Okay, so shear force is measured in the proing ring. Okay, now if you see clearly what is the equilibrium condition of this block. See, it has a small rollers or rails. It means this block will move, and this is a table, top of the table. Okay, this plunger when it moves, you can see here upper, this is the sample and the plate. Okay, upper half and lower half, these pins are removed, means they are ready to move. Okay, horizontally. So here when the force is applied, which is measured here, the displacement of this box is nothing but the displacement of this the soil. The soil will shear at this level. I'll draw the figure. So this is the bottom part of the sample. Okay, so this bottom part moves, then the top part is its own place. Now this is the plane of failure, alpha is equal to 0, and this is how the shear stress is developed, and a normal stress is applied, sigma, and a tau. So the soil is fell into two parts forcefully in horizontal direction. Okay, now you can see the upper part is fixed, this is called as a yoke. Okay, as we have seen here, this part. So upper part slides over the bottom one, and this yoke is connected to the proing ring, and proing ring is fixed. It means the upper part is in the equilibrium condition, the fixed condition. Okay, when force is applied by plunger, that means the bottom part moves. Okay, it is something like upper part and bottom part. The bottom part moves, upper part as it is. Okay. So the stresses are transferred on the soil, and it goes to this failure plane, and maximum stresses, shear stress, that is obtained. The aim is that what is the maximum shear stress at failure under the normal stress. The sample is subject to the normal stress. There is a separate arrangement, just like a consolidation we have seen one frame freely suspended, connected with a lever and the hanger, and those weights are put here, slotted weights. Okay, this principle is same as in the consolidation. I explain how it is a normal stress. Okay, because this lever is fixed here, the plate is fixed, area is also fixed, 6 into 6. Okay, therefore these plates are calibrated in a pressure or stress. These are effective stress, 0.5, 0.2 kg per cm square, 0.5 kg per cm square, 1 kg per cm square. These are the plates available. Okay, so they directly exert the normal stress. Okay, this is called as a loading pad. In CU and CD condition, porous stones and perforated grid plates are placed on either sides. Okay, the first part is the sample preparation. Sample is prepared in two ways, either in undisturbed sample or a remolded sample. Undisturbed sample, mostly for clay samples, are generally prepared in undisturbed state. Okay, these samples are obtained from the site in the UDS tubes, and then there is separate shear ring of size of sample 60 by 60 by 20 mm. This size, it has a cutting edge, and UDS tubes are like your core cutter. They covered with a wax obtained from the site during soil investigation. Then this ring presses inside and cut it without any disturbance. Okay, and then the sample is transferred inside by a pushing plate inside this box, shear box. So directly we get an undisturbed sample. Okay, after arranging base plate, porous stone if required, serration plate, and then sample, cut it here, push it here, again serration plate, porous stone if required, and a loading pad. This is how the sample is prepared for undisturbed test. This is very useful, particularly for a clay type of soil or a C5 soil. We call it a Mohr type of soil, if possible, to get a undisturbed form, because it gives the actual state of stress, soil in situ condition, and we get a more realistic shear stress. Okay, shear stress. Second is the remolded samples, mostly for a sand or silt. You cannot bring in undisturbed form, so you always bring in the remolded form in the bags. And then their density is very important. As I say that C and phi value are depends upon the what is the density or unit weight, their porosity, their moisture content. If they varies, your C and phi value will varies. Okay, therefore they are compacted to the required density, given density. If it is not given, sometimes mention that compact it to the maximum dry density and OMC. Okay, then you have to conduct the compaction test. Okay, and then you know the gamma value and moisture content, you know the volume here, so you fill the sand directly into the shear box. You know the weight, you know the moisture also from OMC and dry density, because you know the volume. The volume of the shear is 6 into 6 into 2, 36 into 2, or sometimes 2.5 also. Okay, so these are that is the volume you get. If it's 0.5, you get around 90. Okay, so this is how the sample is prepared in undisturbed, or the sand or silt generally is filled with a remolded. Now test procedure. Direct shear test is the best suited for the sandy or cohesionless soil under the CD drainage condition, consolidation drain condition. It can be also used for a clay silty soil in a undrained condition also, okay, with some approximation, because you must have seen the setup. There is no wall, nothing. Water can flow, water can leak out through the between these two holes, okay. We cannot maintain the pore pressure also. So the CD condition is one of the best condition, but the time required is very high. But in case of a sand, even the CD condition is much better, because the time required is less. Permeability of sand is CD is very high. So that's why this test is much useful for a cohesionless or sandy silty sample. So test can be conducted in undrained condition. Now in this case, the solid serration plates are used, no pore stones are used, okay. So sample is either placed undisturbed or remolded, as we discussed. Once this is the consolidation ring, and then it is put in that outer box, that is called as a water jacket, okay. Then it is placed in that water jacket, and the space in that also filled with the water. This space is filled with the water, okay, in order to prevent any moisture content to go out, okay, when you apply the normal stress or when you apply the shear, okay, that is the purpose. Now first the normal stress is applied with the help of this slotted weights are placed here. The normal stress is applied. As soon as it is applied, okay, the shear is start, because no time is allowed for a consolidation, because it is an undrained test, okay. So the test should be completed in 5 to 10 minutes, and at least 3 such samples with the same moisture content, same void ratio, unit weight are placed in the box. Separate sample, fresh samples, okay. And the normal stress applied, it is different. Normal stress are applied. For example, sample is placed here. First normal stress applied is 0.2 kg per cm square. Then shear is applied, okay. So this box will move, and shear force is recorded here. Displacement of the this outer box, which actually indicate this delta, okay, is measured here. Because of normal stress and during shear, the sample thickness decreases. That is measured on the vertical stress, okay, change in thickness. So this is called as the shear displacement measured in the horizontal dial gauge, and change in volume or vertical displacement in the vertical dial gauge. Probing ring measure the shear force, okay, and shear force is applied with a certain strain rate, like a 1.25 mm per minute. This setup is called as a strain control setup. There is also a stress control setup, but most convenient is a strain control setup, okay. So sample is first subjected to the, let's say, 0.2 or 0.5 kg per cm square. Then after failure, next sample is placed. Then double the normal stress is applied. Then 1 kg. If it is 0.2, then 0.5. If it is 0.5, then 1. Okay, and third trial maybe 2 kg per cm square. How to decide that which normal stress to be applied, whether it is 0.2, 0.5. When the material is a very loose state, then less value, 0.2 kg per cm square is applied. Material is stiff, higher density, higher unit weight, then higher values are applied. But to simulate with the field conditions, okay, a sample is collected at suppose 2 meter, and gamma value is suppose a 20 kilometer per meter cubes, okay, then it is become 40. total stress is 40. If there is a water table, then find out effective stress. So that should be the a normal stress, that is final normal stress. Earlier trial you can reduce by half. Suppose it is 4, then you can put 2, then you can put even 1 also. Okay, in this way the normal stresses are decided. So here our aim is to find out what is the maximum shear stress. Directly you don't get shear stress, you get a shear force. What is the maximum shear force? Shear force is measured in flowing ring. So what is the maximum flowing ring reading? So that you don't get in one observations. Okay, you are applying slowly the moment of the applying shear force, the box moves. Okay, so it is called a strain control. Okay, with certain rate of strain measure the force in a flowing ring. So as it is an untrained test and it is a test has to completed quickly, around 10 minutes maximum. So the faster rate is applied, and this is adjusted in a gearbox. So the motor applies the horizontal shear at 1.25 mm. So shear is applied on this. Okay, and this is suppose flowing ring on this side, 1.25 mm per. The aim is that no pore pressure is allowed to dissipate, because sample is free to drain, but rate of loading is faster than the rate of consolidation or permeability. That concept is used. That's why it is 1.25 mm per minute is the fastest rate. Okay. So this test has one limitation about the pore pressure, as we discussed earlier. Second type of this test is the consolidated undrained condition. Now as it is a consolidation, the sample is covered with a porous grid plate or serration plate, and porous stones are used. Porous stones are like that. They have a permeability many times of that soil, 10,000 times or more maybe of soil. Okay, they should be a fresh one. They may be a certain material like silicate type. They should be clean. They should be saturated. Okay, before the test. And grid plate is a porous because water has to pass through that, through the porous stones both sides, and it will get drained off. So sample is covered with a porous stone and grid plate. Okay, and then it is placed in the water jacket outer box, and is placed with the water, and then normal load is applied. And then as soon as normal load is applied, vertical dial gauge, it means here normal load is applied, no shear stress is applied, and now this set box shear test is converted into consolidation test. With respect to the time interval, you can measure the displacement. Just like in consolidation, we take a time interval 0.25 minute, 1 minute, 2 minute, 4 minute, like that. Measure the dial gauge. Okay, this will rotate again here anti-clockwise because there is a compression. Okay, in the height. Height may be 20 mm or 25 mm. Okay. So consolidation, once it is over, generally we keep 24 hours, or when there is no change in the reading in the vertical dial gauge for sufficient time, then we say consolidation is over, and then we apply the shear stress. Okay, and now shear stress, during shear stress undrained condition is required, means shear stress is applied at a faster rate, that is 1.25 mm per minute, so that no drainage is allowed, or the pore pressure is not allowed to dissipate. This condition has some limitation about the pore pressure, particularly the granular soil has a more difficulty, okay, in maintaining this pore pressure. Third is the consolidation undrained condition. It is just similar to the setup is exactly same as the CU condition. Sample is covered with the porous grid plates or serration plate and the porous stones on both sides. Here first the sample is first trial. Every condition 3 samples are tested. Okay. So first sample is allowed to here consolidate under the normal stress, maybe 0.2 or 0.5 kg per cm square. You can keep 24 hours or the time up to which there is no change in the vertical dial gauge. Okay. The water jacket must be filled with the water before that, and once the consolidation is over, now the shear force is applied with a very slow strain rate. Okay. And that uh, that strain rate is very slow. That is the consolidated drain test. Okay. So the setup is same. Here only the difference is that after consolidation the shear force is applied at very small rate, that is 0.0125 mm per minute or the less. Minimum 3 samples are tested at a different, usually double the normal stress. As the normal stress is double, the shear stress is also increase. Okay. And both vertical compression and horizontal shear are recorded during the shear also. And so in this way 3 conditions, any one condition is observed depending upon the requirement or to simulate the site condition. Okay. So once the sample is prepared under the any of these 3 conditions in shear bar, it is then transferred in the water jacket, then slotted weights are placed in a hanger. Shear force is measured in the probing ring attached to the horizontal direction. Shear displacement is recorded in the dial gauge in horizontal direction. Vertical dial gauge is placed on the loading plat. This gives the change in thickness or change in volume. Before you start any trial, after the sample is assembled, okay, the upper part of the box, shear box, is lifted by 1 mm. There is a screw to lift it, just to prevent the friction between two metal. Okay, so that a failure plane pass through them. Then entire the setup is mounted on the rollers, because the box moves, expected to be less friction. Then the shear force is applied by electric motor to a constant rate. It has a different gears to adjust the strain rate. Minimum 3 samples are tested under the 3 different, usually double normal stress, and shear force at a constant dial gauge intervals are recorded in a probing ring. Unit weight moisture contents are also recorded after the testing, and moisture content also recorded after the testing also, after the failure of the each sample. So each trial is how long we continue the shearing. When we come to shearing, so it is continued till the probing ring shows increase in the readings and then decrease in the readings. Okay, then you can stop. Sometimes loose sample, this is perfectly ideal for condition for dense sample, but for loose sample there is no peak value, so you get continuously either increasing or then almost a horizontal graph, or there is no much increase in the loop. In that case you can stop the test at 20% strain. That will see how it is. Okay, now let's see the observations. This is soil type, what was the density, what was the moisture content. Okay, then what is the area of sample, that is fixed. Small size is 36 centimeter square. Length and width is 6 by 6. what is the proing ring capacity used, that you have to write 2 ton, 2 kilonewton, 5 kilonewton, like that. Then calibration chapter, as I discussed, every ring has a calibration chart given by the manufacturer, and this calibration has to be revised by every 6 months. Then the dial gauge least count is you must know generally 0.01 per unit, means one revolution gives me 1 M. Okay, so there are 100 parts, so that 0.01 suppose is the dial gauge least count. Now you can see the table, dial gauge readings, that is horizontal, that is for the shear displacement. Okay, then proing ring reading, that gives you the shear force. Then vertical dial gauge, that gives you the change in volume or delta H. Now from this dial gauge, horizontal dial gauge, you can find out shear displacement. How? Dial gauge reading into least count. Okay, then vertical delta H is obtained from vertical dial gauge reading into its least count. Then shear strain is obtained by this delta divided by the length of sample into 100. Length of sample in the direction of the displacement is 6 cm or 60 mm, and delta you are measuring here. Okay, then you get from proing ring reading, convert into the force. This proing ring reading multiplied by this calibration factor, you get a shear force. And now shear force is divided by the fixed area, 36 centimeters square, then kg per centimeter square, you get the shear stress. Okay, as it is a strain control, so this table is for a first sample. Okay, this is for sample suppose 1 and given normal stress. Example, suppose 0.2 kg per cm square. The normal stress is constant for first trial. And now take the dial gauge reading, any interval, try to take close interval, let us say 20, 40, 60, 80, like this you continue. Now when the reading start, for example, first 0, 0, now proing reading shows suppose 12, then 25, 34, 42, 47, and you can see after 47 it decreases again. So when decreases, you can stop. This is perfectly correct for a loose sample, dense sample or over consolidated sample. But for a loose sample, what happens? Like this is 42, 47, then again 47, maybe continue 46, 47, this like continue. Then you can stop. This value as 20% is around say 1200. Then you can stop the test. Okay, that is particularly happen in case of a loose sand or a normally consolidated soil. So this table, what is basically a dial gauge gives me the strain, that is shear strain, shear displacement and shear strain. Proing ring gives me the shear force, and finally the shear stress. Now, vertical dial gives me the change in volume. Okay, now why this table is required? Because we don't know directly what is the maximum shear stress. We require this shear stress. Okay, first is 0, then this value goes on increasing, highest value then decreasing. So what is that highest value? So that's why we are measuring in interval. So this is the typical table. In here I mentioned that the drainage condition is undrained. Now after the observations are recorded, we'll do some calculations.